one more time and then we'll go ahead and then we'll solve the problems on that. Let me share my screen first. Okay. So in yesterday's lecture, we were discussing about electrostatics. We already know that there are two laws of the Coulomb. First law being the like charges repel each other and the unlike charges attract each other. The second law states that the force between, like if you have two positive or negative charge or any charge particle in a space, there are two particles near each other. In that case, there would be some force exerted in between that two, and that value of the force is directly proportional to charge itself, q1, q2, and it is also inversely proportional to the square of the distance between the two charges. And the third point is it is also dependent on in which media the or which is the dielectric media. The constant K is dependent on the medium of the dielectric or the space in which I have put two charges. So we know the value of K is 1 upon 4 pi epsilon 0 epsilon r. Epsilon 0 is absolute permittivity of air or vacuum, and epsilon r is the relative permittivity of the media. If I have considered the space, air or vacuum, please turn off your mic. If I consider air or vacuum, in that case there won't be any epsilon r coming because epsilon r value is 1 in that case. The relative permittivity reference to my absolute permittivity of air is always 1. Okay, that's why it is ER is not present over here, but in any other media epsilon r would be present. So that is relative permittivity of any media. Then we have seen what is electric field, how electric field works. Whenever there is a charge, the force would be exerted in all the direction perpendicular to the charge surface, and that force lines is nothing but your field lines. The line in which the force acts is known as electric field lines. Okay, for a positive charge, electric field line will go outwards. For negative charge, the field line will be coming inwards. Then if positive negative charge are placed in space, the field line will connect start from positive charge and it will end up at negative charge. For the both the same charges, like both being positive or both being negative, in that case each other, then measure the strong, how strong the electrical field is. That is nothing but electrical field strength. How it is measured? It is basically force per coulomb. Okay, what is electrical field? Electrical strength is force per coulomb of charge. Okay, it is always measured in Newton per coulomb. Then we have already also seen electrical flux density. What is flux density? Flux density is basically flux plus, passing through any unit area, or you can say area of a plate or a sphere or whatever, in your case whatever is the object, that area of that object and flux passing through that object is nothing but electric flux density. Then we have found out the relation between this D and electric field intensity, strength E. How we have found out that relation? We have assumed a charge q at some location P, and from this charge q, there is d distance apart, 1 coulomb or 1 unit coulomb charge is present at point A. Now, first of all, I have to find out the flux density at this point A. To find out the flux density at this point A, I have assumed a sphere, a hollow sphere. Okay, then I can find out the flux density on the surface of the sphere. What would be that? It would be flux divided by area. What is the flux in our case? The q coulomb charge will produce q coulomb of flux. So flux value would be directly q. And my area of sphere is always, we know that it is 4 pi d square, because d is here your distance between these two charges. This d is not related to your diameter. This is the actually the d is the distance between my charge q and my 1 coulomb charge. And the sphere, I assume like this, the sphere actually the Radius of the sphere would be d. Okay, see, I am assuming a sphere like this, starting from here. The sphere is like this, okay, and this is the radius of sphere, and the radius is actually my d. Okay, so d is not diameter here. D is radius of the sphere actually. So that's why it is 4 pi d square is the area of the sphere. Then I have find out the electrical field intensity at point A. Okay, at this point, what would be the electrical field intensity? We know that E is equal to F by Q. Okay, E is equal to F by Q. Value of F is Q1 Q2 divided by 4 pi epsilon 0 epsilon R d square. From that, this Q2 is 1. That's why it has been like put as 1, and we know the other values. Now from this, I'll separate out 1 upon epsilon 0 and q upon 4 pi d square. And if you look at this term, we have already see this q by 4 pi d square over here. It is nothing but flux density. Okay, so this is flux density. It is represented with d. That's why I can say E is equal to 1 upon epsilon 0 epsilon r into d. Or inversely, I can say d is equal to epsilon 0 epsilon r times E. Okay, that was the relation between D and E. Then we have seen what is the absolute and relative permittivity. So the ability of dielectric material to permit the electrical field to be passed through it, it is called the permittivity. And whatever this value of this permittivity is actually the absolute permittivity. So whenever I consider the raw example like dielectric material to permit the electrical field to be passed through its uh, is called the permittivity. It is denoted by epsilon, and whenever I say epsilon, it is absolute permittivity. Then for vacuum and air also dielectric materials, and they too have permittivity, and it is denoted by epsilon 0. Or I can say this is my reference permittivity for all the other uh, relative permittivities. So it is epsilon 0, absolute permittivity of air, or absolute permittivity of vacuum. If the value is 8.854 into 10 to minus 12, you have to remember this value because we are going to use this in examples. So you have to mark up this value 8.854 into 10 to minus 12 farad per meter. Then what is the relative permittivity? Relative permittivity, epsilon r, is actually the ratio between absolute permittivity to my reference permittivity, or I can say the permittivity of my air. Okay, so this is the permittivity of air, this is absolute permittivity. So epsilon r, that is my relative, it is nothing the or vacuum, that is epsilon r. Now from that we have come to this some definition. The first being electrical potential, that is nothing but a work done on unit charge, or I can say charge. Whatever is the work done, that is my potential. It is measured in W by Q, work done per charge. If it is unit charge, my work would be my potential. Then we have also seen the equation for the potential difference, VA minus VB. If a point B, some charge is placed at point B, and if I am moving that charge from point B to point A, what would be my potential difference between that 2 points is this Q by 4 pi epsilon 0 epsilon r into 1 upon d1 minus 1 upon d2. And we have seen potential gradient. The change in potential due to the change in distance is nothing but a potential gradient. Then we have seen the dielectric strength of material, the ability of like any material to withstand the electrical stresses is dielectric strength. Okay, if I have an air and if I am putting two plates in air, and if I continuously put charges on the plates, at some point of time the charges would be so high that breakdown will happen, and whatever is in between, like air is in between, it will break down. Literally a spark will jump from a positive plate to negative plate, and that is nothing but a breakdown. So to the whole withstand that up to that particular charge until and unless that breakdown occurs, that is nothing but a dielectric strength of any material. It is always measured in volt per meter or volt per millimeter. And whenever you increase the thickness of dielectric media, at that time your dielectric strength would decrease. We have seen what is a capacitor. Capacitor is nothing but two parallel plates in between some dielectric media is placed. This forms of capacitor. The ability of this capacitor to hold the charges is nothing but a capacitance. The ability is called a capacitance. It is the capability of a capacitor to store charge on it, and it is the charge, whatever charge I place here is directly proportional to the potential difference between that two plates. Okay, so I can say Q is proportional to V, and to remove this proportionality I can put a C, and C is nothing but my capacitance. Okay, C is not a constant, so that is capacitance itself. So value of capacitance can be found out if you know the charges on the plate and the potential difference across the capacitor. Q is equal to CV is the equation. Then we have seen two type of capacitor. First with a uniform dielectric medium, parallel plate capacitor with uniform dielectric medium. What does it mean? That I'll have a two parallel plate, and in between, whatever is in between the two plate is same throughout the surface of the plates. Okay, there would be no difference in here. So this is the first example, and in this example some information is given. So first is the permittivity of media is epsilon r, charges on plate is q, and the distance between two plates is d. That is the basic information that we have, and the voltage across these plates are v. From this we can calculate d is equal to q by a, n is equal to v by d. From this we can have the would be helpful only and only whenever there is a uniform capacitor formulated with a single media. Okay, single media. See, this is a single media. Now what if the two medias are different? So what if the two media is different? For an example like this, here in this example we have two different media in between two parallel plates. Okay, so which are the two media? Okay, so see, this is my plate. This is, let us say this is plate A, and this is my plate B. These are two plates, and in this, between these two plates you can see two different media. This is my first media, okay, and this is my second media. Now you can see it is denoted as epsilon 0. That means this is nothing but an air, and this is represented as epsilon r. That means this is some media that we can have like we can have makeup, we can have oil, something like that. But this is different than air. This is not air. I'm sure for that. So this is some different media. That depends like what you want, whatever you can take. But here for a generalized example, we have taken it as epsilon r, some different media. Okay, but this is epsilon 0. That means this is air. Whatever here is air. Like this is blank space. This is air. So we'll see this as a partly air medium. Okay, so part of the capacitance is formulated by air as a medium, and part of it as something else. So how to calculate the capacitance in this kind of case? So first of all, to find out this, you must know what is the thickness of these two media. So here the thickness of your media is T, and thickness of your air is not given, but actually I can say this is distance apart, T is minus T. Okay, so I know that the thickness of air is D minus T. Now, how to calculate this capacitance? So, whenever you have been given an example of capacitance, we'll always start with voltage V. Okay, so let us assume V potential is applied across this capacitor. In that case, V1 would be the potential appearing between the first dielectric media, and V2 would be the potential appearing at second dielectric media, and V would be nothing but V1 plus V2. Now I can put value of V1 and V2. What would be the value of V1 and V2? We know that E, electrical field strength, E is equal to V by T. Okay, what is V? V is the potential and D is the distance. So we know that E is equal to V by D. So I can put it E is equal V is equal to E into D, thickness of media and my electrical thickness, or you can say distance, and this is my electrical field strength. So I am going to put this V1 value using this equation. So here V1 is nothing but E1, okay, because the stresses in this media and this media will be different. So I'll write as E1, and the thickness I know it is T. So I could put E1 into T plus E2, the thickness of second media is D minus T. So I'm going to put it like this. So this is the equation. V is equal to epsilon 1 into T plus epsilon 2 into D minus T. Now we also know the other relation between E and D. What is the relation? Relation is E is equal to 1 upon epsilon 0 epsilon R D. We know that. So here I am going to use this equation, a value this equation, the D1, my relative permittivity epsilon R and epsilon 0. Okay, so D1 upon epsilon 0 plus epsilon R. Now still there is 1 T, so I am going to multiply it with T plus E2. For E2 I am going to write D2 divided by epsilon 0 epsilon r, but here as this media is air or vacuum, we know that the epsilon r is 1, so I am going to remove this. So it will be only epsilon 0 d2 upon epsilon 0 into d minus t. This is the equation. See, this is the same equation. Once I simplify this equation, so I can get d common. There won't be any d1 or d2. This is one more theory. Whenever there is electrical field, we will see all where there is electrical field will pass like this. Okay, so field strength can be different, but electrical field would be always like this. Okay, and if I take area over here or area over here, in both the cases area would be same, and my flux density will be same because charge would be q. So q and q would be same, would be uniform between these two media. So there won't be any D1 or D2, but actually I'll have a D only. Okay. Then why I have written E1 and E2? How that two values will be separated? It is separated based on this epsilon R. See, you can see here the E1 is actually my D upon epsilon 0 epsilon R, and here my E2 is only D by epsilon 0 because this is air. So in that case the field strengths can be different, but electrical flux density would be same in both the cases. So I can write D upon epsilon 0 epsilon R into T to D upon epsilon 0 into D minus T. So this is the simplification. Now from this I can put value of D. We already know that. What is the value of D? What is the value of D? So we know that D is equal to Q upon A. What is Q? Q is the charge on the plate and A is the area of the plate. So D is equal to Q by A. So putting that equation, D, instead of D I am going to put Q divided by A. So I get Q by A epsilon 0. See, this is that. Q epsilon 0 into A into D minus T. Okay, this has been just simply like this is rewritten like this: D minus T plus epsilon, and for minus. Okay, I have taken minus common, so I can put T minus T upon epsilon r. So that's why you will see it like this: D minus T on epsilon r. But actually these two are inside a bracket, so keep that in mind. Whenever I open the bracket, this will become plus and this will become minus. So it is the same equation. So Q upon epsilon 0a into D minus, in bracket, T minus T upon epsilon r. Now if I take this Q here, I'll get V by Q, and if I take inverse, like instead of that I'll put V over here, I'll take epsilon 0 over there. So my final equation becomes epsilon 0 A divided by D minus T, D minus in bracket T minus T upon epsilon R. And this Q by V is nothing but your capacitor C, capacitance C. So C is equal to epsilon 0 A upon D minus T minus T upon epsilon R. So using this equation, you can calculate the capacitance with two different media, but in case of two different media, one must be an air media. Why? Because we haven't taken epsilon r here, we have directly removed that epsilon r here. So if this media change, epsilon r would be introduced at this place, it would be r, because that in next example. But this is the scenario when I have a partial air as a one medium. Okay, so first one was for uniform capacitance C is equal to epsilon 0 epsilon r A by D. For partially air, we have C is equal to epsilon 0 A upon D minus in bracket T minus T upon epsilon r. This is the equation. If the medium were totally air, I can put T equal to 0. If my air is only air is present here, I remove this. In that case, I can put this thickness as 0. As soon as I put this 0 minus 0, I'll get epsilon 0 A by D. And you can see that it is same like this. Here also, if I put epsilon R equal to 1, I'll get C is equal to epsilon 0 A by D. And it is same here. If I put thickness of the other material 0, or I can say the other material don't exist, in that case thickness would obviously be 0, so I'll get the same equation. So this is the case with partial air. Same way, we are going to have an example with the composite dielectric media. Now, whatever we have done for the partial air media, we are going to do here, but here we have composite air medium. Composite dielectric medium. That means this material is different, this material is different, this material is, let us say this is paper, this is mica, and this is oil. Okay, these are the three different media or three different dielectric materials. For that three dielectric materials, my three relative permittivity is epsilon 1, epsilon r2, and epsilon r3. The stresses, field stresses appearing across each material is E1, E2, and E3, and the total voltage appearing across this three is V1, V2, and V3. And D1, D2, and D3 are the thicknesses of this. Yeah, so the figure is not like greatly represented, but let us try it like this. D2, D3 is the thickness. Okay, I can have 4, 5, 6, 7, or I can have also 2 for the same way I can consider for two different media. Here I have three different media. Okay, so you have to just add one or two terms at the end. Okay, so how we have done in the case of partial air media, same way we are going to derive the equation. We know that the voltage potential difference between each dielectric media would be V1, V2, and V3, and the total voltage would be V equal to V1 plus V2 plus V3. Then I am going to put the value of V as E into D, because we know that V is equal to E is equal to V by D. So from this equation, I can put V is equal to into D. So here my electrical field intensity strength would be different for different media. So I can put E1 into D1 plus E2 into D2 and E3 into D3. D1, D2, D3 are the thicknesses of the media. I can put value of E as D upon epsilon 0 into epsilon R. So here these three media are different. So three relative permittivity F is epsilon R1, R2, and R3. So I'll put it as D upon epsilon 0 epsilon R1, D upon epsilon 0 epsilon R2, and D upon epsilon 0 epsilon R3. Okay, D1, D2, and D3 would be as it is, no change in that. Then I'll take this D and epsilon 0 common from each term, because each term have that thing. So I'll take that common. So I'll get this equation D upon epsilon 0 into D1 upon epsilon R1 plus D2 upon epsilon R2, D3 upon epsilon R3. Then I'm going to put the value of D as Q by A. What is Q? Q is the charge available on the plate. and A is the area of this plate. Area of this plate. So Q D is equal to by A. Once I put into 1 upon epsilon R1 plus D2 epsilon R2 plus D3 by epsilon R3, and we know that what is this equation called? It is nothing but V. Okay, so I can write that's V. See here, that's V. So I can put is equal to V. So I'll put this V by Q, sorry, Q by V, not V by Q. Will come this V on this side, and I'll take epsilon 0 above, and I'll take this whole term in denominator. So I'll get Q by V. Okay, here Q by V epsilon 0 A. Okay, this term going on the opposite side, and this whole term will come in denominator. So epsilon 0 A divided by d1 upon ER1, or we can say epsilon R1 plus d2 upon epsilon R2 plus d3 upon epsilon R3. So this is the equation for the three different composite media. Now if you have given like only two composite medias are there, what would be equation? Epsilon 0 A divided by d1 upon epsilon r1 plus d2 upon epsilon r2. If there are 4 media, you will add one more term epsilon r3 plus 4 by epsilon r4. 5 media, I'll add one more time because this will remain it is it. The number of media increases, the number of times I have to put this term. D3 is the thickness of the new media. So D4 for the fourth media and fourth media. So it would be D4 plus D4 divided by epsilon R4. That way you can find out the composite dielectric medium capacitance in composite dielectric medium. Okay, so this was the this is the how you can do that. Now we are going to have one example. The first example has to be calculated by you, then we'll solve one more example. So I'm showing the question, read question twice and then try to solve the question. It is very basic question. You just have to find out two different capacitance under two different scenario. Okay, any questions up to this slide?
Sir,
Yeah, go ahead. What is that?
capacity.
uh, which capital D? Yes, this D is capital D here. The D
Sir,
is
then here D is Q by A, but
D is
D is
Q
flux by A.
by A. So this Q is actually my flux. Flux is represented by psi, but whenever I talk about flux for unit for any for Q charge, my flux would always be like my psi would be equal to Q. That is the thing. That's why I can directly, instead of psi, I can directly put a Q. That is charge on the plate. My flux will be directly dependent on the charge available. Whatever is the charge, according to my flux will be. So flux would be Q. Okay, this is flux density. So I can directly put D is equal to Q by A. I'll show this somewhere. Let me show it to you. See here. We have this electric flux in coulombs. Okay, we know that what is the charge is it, Q is the charge in coulombs, so it is actually the same thing. Whenever you've been asked flux, you just have to put the value of the charge. So here I am putting Q by A. Okay, so psi is equal to Q. I can say that psi is equal to Q. That's the thing. Anyone else? Any other question? Yeah, go ahead.
Sir, how is electric field equals to D by epsilon 0 into epsilon R?
uh, E is equal to D by epsilon 0 epsilon. We have seen that relation in yesterday. Let me show that to you. We had yesterday using we have that, and we have solved this. Like just go through this two slide and you'll see that what we have done here, and at the end we get this equation. E is equal to 1 upon epsilon 0 into epsilon R into D. So from this relation between D and D, we can put it out there. We have done this yesterday.
Yes, sir.
Yeah, anyone else? Okay, then we can go ahead with the example. I'll show you the question. Try to solve it first. Okay, and then let me know the answer. I'll put the answers later on and how to solve it. It's very basic question. You can easily do that. This is the question. Try to solve this question.
Sir, distance between the plates.
This is already given distance with. See here, the question itself explains everything. A capacitor is made of two plates. Capacitor is made of two plates with an area of 11 centimeters square. Okay, so that is actually there are two plates. The area of this plate is 11 centimeters square. Are separated by a mica sheet of 2 mm. So these two are separated by mica sheet. So there is media in between here. This is mica sheet and it is separated by 2 mm. That means the distance between these two plates is nothing but 2 mm. And related is given as 6. So this is the basic information from which you can calculate your capacitance, and this is the equation that you are going to use. C is equal to epsilon 0 epsilon r divided by T. So if you put values in this equation, epsilon 0 would be, what is the value of epsilon 0? 8.85
8.85 into 10 to power
minus
minus 12.
epsilon r is 6. Now the main thing is this area. Now see, whatever you put here, epsilon 0 is in Faraday per meter. Okay, so this is in meter, this area is in centimeter square, and your thickness is in mm. Okay, so this quantity is in mm, this is in centimeter square, and this is in meters, like per meter. So you have to make sure all the units are same. So you have to convert it either this in meter, or you have to convert Faraday per meter into Faraday per centimeter, Faraday per millimeter, and according to that you have to convert this d into either meter or centimeter. So the easiest option is, let it be as it is, epsilon 0 it is. I can convert this in centimeter square to meter square, and d in millimeter to meter. So how to do that? We know that. How to do that?
Sir,
Yeah.
change in capacitance 2.1 into epsilon naught
Sorry, change in capacitance.
is 2.1 into epsilon naught.
2 point, uh, 2.1 into,
Epsilon naught.
okay, like this.
Yes.
The value of this is already given to you. Like, you know the value, you can put this value. It would be easy in that case. What is the value of this? Value of this is 8.854 into 10 to minus 12 farad per meter. We know this value. So you can directly use this value and get me a simplified answer. Without,
It's 11.6.
without the air, my answer would be this: 29.21 picofarad, and with the air gap, the answer would be changing.
11.6
11.6. Let us,
picofarad.
how to calculate with the air. So see, here I have partial air, but as the thickness of both the media is directly available, as the thickness of both the media is directly available, what I am going to do here is I'm going to directly use this equation: epsilon 0a divided by d1 upon epsilon r1 plus d2 upon epsilon r2. Now, like, I have the epsilon r2 value, but for air and vacuum, epsilon r2 is always 1, or epsilon r is always 1. Relative permittivity is 1 for air and vacuum. So here I'll put 0.5, and directly I can put 1 here. And by solving this equation, I can get the other value is this 11.68 picofarad. But you have to keep in mind this meter centimeter. Otherwise, rather than getting this, you will get 29.21. No issue in that. But you won't get this pico. Instead of pico, like pico is 10 to minus
12
12.
minus 12.
12 minus
okay.
12.
Okay, so instead of 10 to minus 12, you might get 20 to minus 11 or 20 to minus 5, minus 6, something like that. So you have to keep this in mind. This must be in meter square and this must be in meter. Now, how to convert this in centimeter to meter? Like, centimeter to meter, what we know is sorry.
Sir,
Yeah, go ahead.
in we are moving in change in capacitance. We can also use that formula for specially made for air.
We can use that formula, no issue in that. You will get the same answer in both the cases. But that formula is little bit complex. Like, if you have both the thickness available, we can easily do this with.
2 mm mic, 0.5 mm air.
We have that, but in that example, in that calculation, what we have done here, if you look at this closely, here this equation, here this equation, yeah, here this is the final equation. and this equation, this d is nothing but the total distance between two plate. Okay, so if I have 2
2.5
mm
mm.
of thickness of my media, then I'm moving my plate by 0.5. So actual I have to put this d as 2.5 mm. Okay,
Yes.
and then I can put this t as 2 mm. This t would be 2 mm, and the answer would be same in both the cases. No change in the answer. But instead of that, directly what I have done in this case, I was knowing this d1 and d2 separately. Okay. So instead of taking this ER2, what I have done, ER2 is 1, I know that. For air, my epsilon R is 1, or I can say relative permittivity is 1 for my air and vacuum. So I directly use this equation and I have put this as 1 directly. That also works. Whatever method you prefer, you'll get the same answer and it won't matter.
Yes.
Anyone have issue, like anyone have trouble in converting like centimeter to meter or like millimeter to meter? It should not be trouble like that. It is very basic thing. But if you have trouble, you can let me know. Okay, then we can move ahead directly. I'm not going into that, and we'll solve one more example. I'll also show the solution this time. The question is, a parallel plate capacitor has plate area of 4 centimeter square. Okay, so plate area is given. A parallel plate capacitor is there. So this is the two plate. Area is given. The area is 4 centimeter square. So it is written as cm2, but actually it is square, cm square. The plate are separated by 3 slabs of different dielectric materials. Now these two plates are separated by 3 different dielectric materials. So I can put 2 lines like this. Let us say this is my first media. Let us say this is my second media. And let us say this is my third media. So there are 3 different media. Okay. The thickness of this 3 media is given 0.3, 0.4 and 0.3. All are in millimeters. With relative permittivity of 3, 2.5 and 2. What you have been asked, calculate combined capacitance and dielectric stress. So you can easily get combined capacitance. How you do that? We know that C is equal to epsilon 0 into A divided by d1 upon epsilon r1 plus d2 upon epsilon r2 and d3 upon epsilon r3. The equation for the combined capacitance, we know that. So from that equation, you can easily solve the problem. Okay, so this is the basic information given. Then from this equation, if I solve this equation, I can easily get 8.64 picofarad. This is my answer of capacitance. Then along with that, I have been asked one more thing, and that is dielectric stress. Dielectric stress is nothing but your electrical strength, like electrical field strength. You have to find your E. And now it is asked dielectric stress is actually you have to find out E. This is a dielectric strength. So you have to calculate that dielectric strength. How to do that? So first of all, we must know what is the charge available on my plate. So first I'll find Q. From this Q, I'll find my D. How? We know that D is equal to Q by A. And from this D, I can get my E. E is equal to epsilon 0, 1 upon, sorry, D upon epsilon 0, epsilon R. So this is the way I can get my E. Okay, but there would be not single E, that would be 3, like E1, E2 and E3. For the each separate material, my electrical stress will be different across each material. So there will be E1, E2 and E3. Okay. Now here the question is how to find out this Q. We know that Q is equal to C into V. Okay, we know that Q is equal to C into V. But issue is that V is not given in entire question. If you say closely, potential is not given. So in this kind of scenario, you can assume the potential. And here, first thing I'm doing is supply voltage 100. Calculate the charge on the plate. Okay, if it is given, no issue. You will get the same answer. But if you are assuming, someone might assume 100 volt. It is possible. Someone might even assume 10 volts. It is possible. So answer will change according to your assumptions, but the method would be same for the all. Okay. But most of the time this value is given. In some cases this value is not given. Okay. So I am getting this Q charge on my plates. It is C into V. Okay. So we know that C is the value of capacitance. So this is my total charge available on the plate, and from this Q I can find out my flux density. D is equal to Q by A. We know that area, so I get D is in coulomb per meter square. Okay, so this is my flux density, and from flux density, using my relation between electrical field uh, strength and flux density, I can get the value of epsilon. I can get value of dielectric stresses, or I can say field strength. Okay, field strength for each material would be different. Like there would be three different field stresses operating over this three material. Okay, for air the electrical field stress would be different, for the mica it would be different, and for some third material it would be different. You have to calculate all three, but here I have only shown you the first one, electric intensity for dielectric media 1. It is E1 is equal to D upon epsilon 0 epsilon R1. Same way you can calculate for the other two material, and the equation would be E2 is equal to, now field density would be same, epsilon 0 would be same, only changes this epsilon R2 will change. For 3 it would be epsilon R3. This will be changed, and I'll get something in kilowatt per meter. This is how you can calculate the example. So we'll stop here for the today's session. If you have any question, you can let me know, or you can leave the class. One more thing, I have not said the assignment yet. I'm busy in some short by tomorrow. Don't worry about the assignment and question bank. I'll say it as early as possible. Any other questions?